Hey everybody, this is Larry. This is me going with Q4 of the recent Leetcode Weekly Contest 220, checking the existence of edge length limited paths. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem and just in general. I usually go over my thought process first during the contest, so I solved this during the contest live, and we'll go over the solutions as well. Yeah, and let me know what you think. So for this problem, what actually happens is that I think I solved a similar problem on binarysearch.com, also something that I recommend you checking out in general. Not a sponsored ad or anything, it's just I'm a fan. But yeah, so there was a similar problem, so I am able to get this quicker than I would have otherwise, because even though I think I got it the first time around, I was a little bit slower before I noticed one thing. The one thing that I would notice is that even though, and this is a critical thing to notice because I don't know if there's an easy way to do it. Maybe there's some stuff with binary search, but I think the constraints are a little bit tight that I wouldn't trust it. But the idea is, the core idea behind this problem is that even though you're given queries in order, you do not have to process them in order. And what does that mean, right? Well, it means that, it means what it means, and I'll come back to that in a second. Let's kind of think about this problem and think about it naively first, right? So naively for this problem, how would you solve it, right? Well, it's just a connectivity problem, and connectivity problem have a couple of ways to go about it. One is depth first search, breadth first search, union find, and I guess those are the big ones for me. And you want to be able to answer queries as quickly as possible. But now for this problem, there is a little bit of a quirk, which is this limit thing, right? And also distance, which is governed by limit. So in this case, well, what we want is kind of think about the process of building out this connectivity graph as we construct a connectivity tree from the edge list, right? And that's basically the idea that I would think about. And even though it's not really a minimum spanning tree, that Cusco algorithm is still handy in figuring this out, because for me, what I thought is that, okay, let's say we are able to answer if we are forced to answer queries live and therefore the inputs are in any order, then there are tricky things, but you have to figure out how to, maybe have some pre-processed answer, and it gets tricky, right? Maybe there's some like inner outer tree, a union find tree type solution. I don't know, right? That's just a much harder problem to begin with. But the way that I think about it is that, okay, if you record the Cusco's algorithm, where first you sort it by distance, and then this is just a visualization. Maybe I could have more visualization with drawing on tools, but sorry, I'm on a cheap laptop, so cheap 6-year-old laptop, so I don't really have any of these tools. I need to figure out. But basically, you can think about, okay, in Cusco's algorithm, is that you at the very, very beginning, you have all these nodes, and actually just minimum spanning tree algorithms in general, but going to go by Cusco's, you have all these nodes by themselves, right? And then as you add in more edges, the tree becomes the forest of nodes just becomes more and more connected, because as you connect edges and then edges and then edges, they become more and more connected. And in that sense, you are able to kind of get that sense, right? So I actually am going to try a little bit. I know that this video is a little bit slow, but maybe you can fast forward a little bit if you really worry about it. But yeah, so I'm going to just visualize a little bit for you. Visualize a little bit for you the sorry, I'm just pulling up the thing, the minimum spanning tree things. But basically, you have some nodes. Let's make the color not quite. Yellow is terrible. Okay, so yeah, so you have some nodes that's and then in the Cusco's algorithm is that you sort it by the smallest weights. And that's kind of the way that's key to this problem is that you eventually connect these nodes together, right? And this is in progress. And the key thing to know for this problem is that as you kind of add these edges one by one, these snapshots in time has a meaning, right? And meaning that another way to phrase it is so let's say let's give an edge weight. Let's say this is 1 and this is 2, and we going increasing order. Let's say that we have this edge and this is 4, and we haven't added this yet, right? Well, what does this tell you right now? And obviously the other edges aren't even added as well because they're bigger than 4. Well, what this means is that this is the connectivity of the graph if every edge in the graph is less than or equal to 2, right? And once you're kind of able to visualize this, well, then there's your answer, right? Because now that means that for every query for which the limit is, I guess, greater than 2, for each limit is 2, it could be off by 1, but you get the idea, which is that given each of those limit, this is the tree that we care about, right? Or this is the connectivity graph that we care about because the other stuff doesn't come in. So then here, if we have a way to make quick queries, then that will give us the answer because you can look at this graph as this connectivity graph as just with all the edges greater than 2 removed, so that if you think about the limit as less than 3, then this would be your graph, and that's what it'll look like. And then you can answer like, okay, well, if I want to check whether this node is connected to this node, well, we could check in quick time, and also this node and this node, right? Like now if you have union find, and the prerequisite for this problem is union find, so I am not explaining that here per se because it is something that is out of scope for this video because it's more fundamental and it is a Q4. But once you know union find, then you're able to do these queries very quickly in either log n time or even log star n of time and effectively constant. Okay, so basically that's how I solve this. Is that I incrementally add to the connectivity graph all the edges under a certain length, and as I keep on doing that, I go through the queries and go, can I answer this query? If now I can, then I answer it because it contains all the edges that are strictly smaller than this limit. And we'll go over the implementation now, so don't worry if this is a little bit confusing. Hopefully that makes sense, and we have these pretty graphs. But yeah, and this is a little bit tricky to kind of, it's almost like that problem where you have 2 sorted away and you have 2 pointers and you go one by one. That's essentially what I did. So yeah, I basically for each query, I keep track of the index so that I can return the answer in a consistent index kind of way. I take the P and the Q, which is defined in the problem, and the limit of that thing, and then I just put it on all the limits, all the queries with the same limit together into in a list, and then I just keep track of the keys to use later. And I also keep track of the number of queries so that we can generate the answers that we need, just with a placeholder, but that's okay. And then for each edge in the edge list, I do the same thing where for each list, I look at the distance and I put all the distances or all the edges that are of that distance together in the list. And this is actually a data structure that I don't use that often, or maybe even at all. So like the way this is using this way of edge list, but it makes sense in terms of Cusco and minimum spanning tree, though this is not strictly speaking a minimum spanning tree problem, but that's how I visualized it. And this is just standard union find. If you watch me solve it during the contest and the video afterwards, I type this live. I don't, because I get a lot of questions about whether like I have a template that I copy in or something like that. And to be honest, I guess if I had copied it in, I would have finished a little bit higher, but that's okay. I'm trying to actually focus on the learning, and so I actually typed this all during the contest, just for the quiz. And then this is pretty much it, right? This is 40 lines of code. This is pretty tight, but now for each query that we have to answer, I look at each connectivity event, and I go, or each edge, and basically I look at each thing. I go, okay, and actually it doesn't actually have to be. Now that I look at it, it actually doesn't have to be in this data structure. It could have just been sorted, and I could have just make sure that this is less than the event. But so my code is a little bit more complicated than it needed to be. But it was because initially I thought I would do it the other way around, where I did the other way around, where I process the edge and then I look at which queries I can answer. But then I was like, okay, it's actually easier the other way, where for each event I process all the edges that I can first. So the code is a little bit weird for that, but that's okay. But yeah, and then now I basically look at all the edges. I mean, this is a for loop that. This is a while loop, a for loop that does that, which is that for all the edges that are smaller than the query that we're asking now, and keeping in mind that these events that the queries, we also sorted by the keys, which is the time that, or the limit that is given, right? So this is the key. These are the keys. So we sorted by the limit. So the limit is going to go in a strictly increasing order, from smaller to larger. So once we do this, so this is only going to go up slightly as we build up off that, and we basically just do a basic union of the two nodes as we pop off the edges, and then at the end, for each of these queries that have the same event, I just go, okay. Actually, now that I think about it, to be honest, I don't need this weird data structure. I could have just sorted them, and it'll be okay. I just need and I could just change this while loop a little bit. But yeah, well, maybe I could have saved a minute or two. But the thing is that sometimes that requires proving, and I wasn't sure about some invariance of the loop. But in any case, for each query, this is a simple union find query for connectivity, which is whether the parents are equal to each other, or the root of the union find tree of those nodes are equal to each other. Because if they're the same root, then that means they're the same node. So then we set that to the answer and keep putting it into the right index. And that's pretty much it. Yeah. So what is the complexity of this? Well, we definitely sort all the queries. So it's going to be Q log Q. We sort all the edges as well. So it's Y log Y as well. Union find. I mean, so this loop is a little bit tricky to analyze per se, but union find and union, because of path compression, it's roughly speaking, let's just say log n for now, or log y because y is the number of edges, or no, n because n is the number of nodes. It's a little bit hand wavy, but it's a good upper bound. It's not a tight bound. And in that case, well, for each edge, we're going to do log n or log v operations. So this is going to be y log v, and then for the find operation, let's also say that this is log n for the sake of y's. For each query, it's going to be log or q log n as well, because there are only n nodes in the thing. So let's put it together. The complexity is O of q log q plus, and this is sorting the queries, y log y, which is sorting the edges, plus for each query is n log n because we do a union operation, plus y log n because we also do, for each edge, we also do a union operation as well, right? So that's your complexity. You could rewrite it and reduce it if you like, but that's your complexity, roughly speaking. In terms of space, Well, it's just going to be linear in the size of the input, which means it's Q. We have one element. We restore each element, which is in Y, though technically, if you're okay with changing the input, you don't need it, but it's going to be O of log Q plus Y because we put them in a different array. But I think if you want to sort them in place, then some of that is not necessary, though of course you still need O of V for the parents and O of Q for the answers. So yeah, so your mileage may vary. So it's going to be at least O of Q plus V, I think, but the way that I did is O plus another Y, though maybe you could get away without it if you're really, really careful. Though for me, yeah, that's how I did it. Cool. Let me know what you think about this problem. It's tricky. It involves one kind of observation that is not, that's a little bit weird, and I don't know. I always find this a little bit weird, which is that when you could take, you take the queries and then you don't have to do them in order, that and you sort them in a way that makes solving them in a much easier way. I don't know how I feel about that, because I feel like queries are a little bit weird, because if you're thinking about doing online queries, then like you can't do that obviously, but but for this problem it's fine, so I guess it is what it is. But yeah, let me know what you think, and you could watch me solve it live during the contest. Let me scroll up a little bit so you can see more. Now. Good. That one was a tricky one. Wow, 4 periodic contests. Okay. Multiple edges between two nodes. A lot of queries as well. Wait, what? Let's say each edge on the path is strictly less than k. Okay. How do we do this? We want to query. Okay, so I mean this is just a lookup reverse pre-calculated MST, something like that. That's not that bad. I mean, it might take me a long time, but it's not that bad. Okay, so queries. What is PQ limit? There's a path between P and Q. Okay, so for each of these, what do we want to do? Well, we want to go sort by limit. Okay, basically what we need. Maybe. Okay, and then now, maybe. Actually, maybe I want to do it in a different way. So now we can do limit is equal to, okay, then we don't even need to sort. And then now we look at each edge list. Would you be in okay, we're going to sort back. Okay. You go to because technically we could also just sort by the third element, but that's fine. Yeah, let's do that actually. Okay, and then now, okay, for the, okay, last is equal to 0. Okay, and we have an answer array. Okay, Q is equal to length of queries. Answer is equal to 7 times Q. Oh, and then we have to write the union find, which is oh, they give you n. Just trying to find out, but I need to figure out n. Okay. For how do I want to do this? Yeah, let's do this as well, actually. And now we go the limit could be big, so we have to be careful actually. Yeah, that's annoying. Let's make it a deck so I don't have to keep track of the index. This as well. No, this is fine. Okay. Now for define and use. Actually, maybe we want to do it the other way. In the queries. So now we go, okay. While length of e key. And the first element is less than the event, or less than or equal to event. sub. Now is you top pop left. I'm a little bit slower than I would like, to be honest, but that's fine. Just trying to make sure I get it right. Okay, so now for you to decide. Okay, and now that this is done, for we limit in as query sub event, answer of, wait, should be an index somewhere. Queries. Oh yeah, the limit is already the event, so index, oops. Index is equal to just boolean, right? Yeah. You find of u is equal to you find of v. And that's pretty much it. True, true, nope. That's not right. That's weird. Limit is 2, okay. Let's go. Dang it. Process 2 first. 1 and 2 is right. Is it strictly less than or strictly less than? Okay, that's why. Then actually we want this to be the case. Okay. False, true, true, false. Not 100% sure, but let's go. Okay. Whew. Hey, thanks for watching this video explaining the problem. Let me know what you think. Ask questions, because then I can answer them preemptively, or join the Discord. Hit the like button, the subscribe button as well if that works, and hopefully I'll see you again. Bye bye.